My name is Rachel Coit, and I am a geoscientist, an environmental geochemist in particular. And what that means, environmental geochemistry, is that I think a lot about the chemistry of the Earth, how the chemistry of the Earth is affected by human activities, and how these Earth chemistry questions also affect human health. So, for example, if we look back 800 years ago, we can see in the bones of farmers and peasants that there is all of a sudden an increase in the concentration of lead in a lot of bones from that period in Europe in particular. And this is related to human mining of lead activities increasing. And so lead, as we know, is a toxic element. And so these mining activities, humans using and exploiting lead for different projects likely affected human health, and we can see it as evidence in the fossil record. But we can also see evidence in ice cores of this increased mining activity. And this mining activity would have been much more small scale compared to what we see today. And so this is really the domain of the geoscientist, of the environmental geochemist. And it relates really nicely to the topic that I want to talk to you guys about today, which is the critical minerals for energy transition. And I want to talk about some of the challenges we're facing here, as well as some of the opportunities that I see going forward. All right. And I'm going to start today by defining what I mean by the energy transition. I recognize that this is an audience that maybe is a little bit less familiar with some of the geoscience world and the way that we talk about things. I'm going to move on to talking about what the critical minerals are when we look at the energy transition, as well as, again, challenges and opportunities that I see in this space. When I talk about the energy transition, what I'm meaning is the transition away from fossil fuels and to more renewable sources of energy. And though I'm going to be talking a lot about energy and energy infrastructure in this talk, I think that much of what I'm saying is actually applicable to computing context when it comes to the mineral. The requirements of the mineral needs are going to be kind of similar. There's going to be a lot of overlap there. So from a computer perspective, this might be interested to people that are interested in hardware and hardware sourcing. With the goal of moving away from fossil fuels, I wanted to show this image of the United States energy consumption by energy source to really give a sense of how far we have to go in order to make our Paris Climate Agreement goals and our world goals of eventually having a carbon neutral economy. We can see really when we look at our larger energy picture in the country that renewable energy and nuclear power, which are both low carbon sources of energy and really what we're going to be moving towards when we talk about this energy transition, they make up a relatively small percentage of our total energy consumption. And so we have a long way to go if we really want to make a full transition towards these two categories. When we look at a global picture, the story is not much different, right? So globally, we see that coal, oil, and natural gas still make up, the vast majority of energy consumption across all sectors for the world. So we have a long way to go from both a United States perspective, but also from a global perspective. What does it mean when we talk about replacing fossil fuels? So what are we going to be replacing fossil fuels with? This is going to be varying a lot by sector. For example, when it comes to the transportation sector, electric vehicles are going to be a big part of this. And related to electric vehicles is electrification. So electrification means that instead of powering things directly by fuels, such as gasoline, or in the case, many of you may have gas heating at home or gas cookware, converting those over to a fuel source. And by electrifying, we can ultimately use more renewable sources, such as solar, wind, and nuclear, or more low carbon sources, to power these other facilities that we weren't powering before. So what are going to be the mineral requirements to actually fuel this energy transition? When we talk about fueling fossil fuels, what you need is to burn a fossil fuel itself. You don't need that type of fuel for low carbon energy sources, but you do need a lot of mineral inputs in order to build these infrastructures. So I'm going to start by showing several graphs from a really wonderful report that was done by IEA, the International Energy Association. They have a really fantastic report on the mineral needs of the energy transition, and I highly recommend anyone who's interested in this topic to check out that report. Here they are comparing the mineral needs for an electric car versus a conventional car. So even though we know that an electric car over its entire life cycle is going to have a much smaller carbon footprint compared to a conventional car, its mineral footprint is many, many times higher, especially for elements like copper and manganese, but also for elements that really aren't used much in conventional cars. These include things like nickel and manganese. When we look at different ways of generating electricity, we see a similar pattern here. So comparing, say, natural gas produced electricity to wind produced electricity, we can see that we have larger amounts of different types of minerals that are needed, but also different types of, but you do for a wind farm. So these types of minerals are going to change that we need, but also the amounts are going to increase many-fold. And I'm going to leave with this final, I'm going to leave this topic with this final sort of image, which talks about how much, if we do actually meet our renewable energy goals in 2040 globally, as per the Paris Climate Agreement. Relative to our uses in 2020, we're going to need over 40 times as much lithium, 25 times as much graphite on a global scale. So the sheer amount of these minerals that we will need to be producing in order to meet these goals, it's pretty astounding. So I'm going to start with some of the challenges. And many of you could probably guess, based on some of our news recently, that supply chains are a big part of this. So a big issue is that the production, so the mining component, as well as the processing, so refining that mined ore, these activities tend to be quite concentrated into certain regions geographically, and the supply chains can be incredibly complex. I'm going to take cobalt as a good example here. So cobalt is needed for batteries in particular. It's also needed for some type of magnet applications. And 64% of the world's cobalt in 2017 was produced in the Democratic Republic of the Congo. This is a problem because this is a region that is quite unstable. And so there's a great deal of vulnerability in this chunk of the supply chain. Not only that, but once that mining is actually done, it's sent to China to be refined. This again could have some implications for supply chain issues depending on a geopolitical context and future uncertainties. The complexity can get, it's very dynamic as well. So for example, rare earth element mining, which has been done quite extensively in China in the past, and China has the greatest amount of refining capacity for rare earth element mining. For example, even though the United States has pretty decent production of rare earth elements, we send almost all of our refining capacity to China. But there used to be a great deal of concern related to rare earth element mining in China, related to human rights abuses, as well as certain types of illegal mining and environmental concerns. In the last 10 years, there have been tremendous gains in government oversight, as well as increased quality of the mining done in China. However, with that has also increased the costs. And so recently, in the past few years, we're actually seeing a lot more of that rare earth element mining being done in Myanmar, as opposed to China, where there is a lot less oversight and a lot less transparency in the mining process. And so while we can make gains in one area, it can be quite difficult to deal with the economy of all of this. There's also pretty long development lead times for many of these operations. So in order to meet environmental standards, in order to meet geoengineering standards, some of these mine operations can take upwards of 16 years to actually fully realize. And so if planning doesn't get started now, when the supply chain pressures really ramp up in different locations, it's going to be hard to get them started on short notice. And then finally, there are also some social and economic barriers that we need to look at. So while many places in Europe, Australia, the United States, mining these materials or refining more of these materials, as we've talked about, there are economic disincentives from doing so in these countries, but there are also social disincentives from doing so. Two examples from the past few months have been rare earth element mining in Spain, which has gained a lot of protesters, especially from local farmers in the area who don't want mining to occur and potentially impact their farming operations, as well as in the United States. The United States has a few lithium deposits, which could provide some much needed lithium domestically, but these operations have come up against a lot of local resistance because of concerns about environmental impacts from these projects. And while I understand that it's quite frustrating to hear these, mining is something that comes with costs. And so some of these local concerns can be quite reasonable. From a global perspective, there are a lot of social concerns with mining. So this image in the background here is from the Democratic Republic of the Congo, where we're seeing artisanal cobalt mining. Cobalt is mostly mined at this point actually as a byproduct of copper mining. So they take the waste from the copper mining and then they refine that waste product into cobalt mining. We have these small scale operations to do a lot of this type of mining. Artisanal scale gold mining is also a pretty large operation in many parts of Africa and South America. And there's a lot of problems with this type of mining because it can be pretty damaging to human health and local environment. There's very little regulation or oversight. In Peru, for example, where you have a fair amount of artisanal scale gold mining going on, you can see that local population, which is not involved in mining, still has high concentrations of mercury, which is an element used in this mining, in their body, even if they have very little connection to the mining operations. Certain countries where this mining is occurring also have pretty big social concerns surrounding the mining operations, including use of child and slave labor. So companies which hope to source their minerals in an ethical way can run into a lot of barriers doing so in a way that is both ethical as well as cost effective. So it can be hard to turn away low cost options on the basis of the way that mining was done. There's also a lack of transparency in many of these places concerning some of the social concerns around mining. We also see the issue with decreasing ore grades in many places that have traditionally been producing a lot of the minerals that we use. So some of the largest copper mines in the world, for example, even though they still have a good deal of copper left, the actual grade of that copper is decreasing. So you're getting less bang for your buck when it comes to the amount of copper you're getting out per unit energy and per dollar that you're spending towards mining that copper. And then finally, and this is something that's quite near and dear to my heart, is that we still have fossil fuel legacies to deal with. Even though we're hoping to transition away from fossil fuels, we still have abandoned mine sites as well as combustion residuals, such as coal combustion residuals, that are a huge environmental problem in many areas. So now that I've covered a bit of what we're worried about, I want to talk about some places that I see opportunities and ways that we can find room to do things better and to build more sustainable and resilient systems. And the first is on the technology front. There's a lot of room for innovation and efficiency in this space. So when it comes to mining, for example, we're seeing a lot of people gaining interest in using former waste streams as sources of new minerals. Two really good examples is in Australia, where there's been a quite amount of copper mining in the past. People are now looking at some of those waste storage facilities and waste streams to see if cobalt can be recovered from those tailings. Also in the United States, where we have a great deal of legacy fly ash, but also coal mines, there might be ways to remove rare earth elements from those waste streams. So new innovation in those spaces to try and find ways to get minerals in perhaps unconventional ways, in ways that we haven't looked at before. There can also be innovation in the space of the technologies that we're implementing. A good example here is photovoltaics, which we used to rely on a great deal of silver to make PVs, but we've really cut down on the amount of silver used in these, and by replacing them with other materials, we've driven down the cost of solar in many, many ways. And then finally, thinking about better recycling practice and in a larger scale, more circular economies. So designing products in a way that we can more easily remove the critical minerals that we're hoping to remove from them, building materials that can more easily be repaired and reused, and building better recycling facilities to more efficiently recycle and truly recycle these materials as opposed to downcycling them. I also see a lot of opportunities in the mining space. And in particular, I'm hoping to see us learn from some of our past mistakes to do a better job in the future of mining these materials, both from increased environmental standards, increased social standards, as well as governance standards. So learn from a lot of our mistakes of fossil fuel mining and build a future mining economy and a future mining system that is a lot better than what we've done in the past. With that, here's my contact info. If you're interested in this subject from more of a in-depth geological perspective, especially when it comes to environmental legacies of energy-related mining, as well as where we're going to be looking at in the future when it comes to lithium mining, cobalt mining, etc. I encourage you to attend the Geological Society of America's conference in October, where we'll be hosting a session on this topic. I'll also take any questions at this time.